Okay. So, last time I was finishing up um, our discussion of, our third pillar of geometry by talking about the Quaternions, because defining the Quaternions allowed me to define the Quaternion projective plane, which gave us an example of a non-Papian plane. And so we we have RP1, which is a real projective line, so we understood that just fine. We have RP2. So RP1 is a one-dimensional projective. This is a projective line. We've been talking about projective planes in this last chapter, so RP1 has kind of taken a back seat. RP2, of course, is a projective plane. All these planes we're going to be talking about are projective planes, but it's a projective plane that satisfies both Pappus and Desargues. So this allows for the construction. So this satisfies Pappus and Desargues. And so the construction that we did of coordinates, of constructing coordinates on our projective plane without the use of numbers, right, was something that we could do. So this construction works perfectly fine in RP2. And in any projective plane where Pappus and Desargues are satisfied, we get our construction working perfectly fine. Similarly, we can follow the same kind of program as we previously defined RP3, this generalization of our projective plane to higher spaces. Well, all of these actually satisfy Pappus and Desargues as well. We can similarly talk about CP2, which is our notion of the complex projective plane. So this is the exact same construction as RP2, except the underlying field is the complex numbers instead of the reals. And so we can do the similar construction of CPN. Well, we did this actually, for any field, including finite fields, which is what led to our construction of the Fano plane. But in particular, this last time we defined the Quaternions. So we had the Quaternions themselves are not a field, of course, because they don't satisfy the commutative property. But this Quaternion projective plane, so this Quaternion projective plane it is a projective plane, so it satisfies the projective plane axioms, but it is non-Papian, so it satisfies Desargues, but does not satisfy the Pappus theorem. Okay, and so thus our multiplication, this construction that we had, is necessarily non-commutative in RP2. And so our program of coming up with coordinates is flawed in this way. The construction of multiplication we have would not be commutative because of this fact. But this satisfies Desargues. And similarly, we could write up Quaternion projective space in the same way. And this quaternion projective space is also going to be non-Papian, because in the same way, if it weren't, then the underlying space that we define this projective space over, the quaternions, would have to have commutative multiplication, but it doesn't. Okay, I'm going to have you all work through in detail notions of the quaternions in your next homework. This is going to help what we do at the very end in these last couple of chapters, because we're actually going to deal with quaternions again in chapter 7. Anyway, so we can do this also for quaternion projective space just as well. So the next thing, as part of your homework, you had to deal with the molten plane, which I don't have notation for, but the molten plane is a projective plane that is non-Desarguian. Okay, so it's non-Desarguian. So it's a projective plane, but neither Pappus nor Desargues theorem is satisfied. And I mentioned last time that Pappus implies Desargues. So if Pappus' theorem is satisfied, then so is Desargues' theorem. So that's why if you have a non-Desarguian plane, it's automatically non-Pappian. For that reason. Okay. But actually, there's kind of a more natural construction of a non-Desarguian plane, even though this works perfectly fine. So there is what's called the Octonian projective plane. So just like we constructed the quaternions, so recall for a second, these quaternions involved numbers that looked like A times 1 plus B times I plus C times J plus D times K, where these I, J, and Ks you can think of as being like the I, J, and Ks from, Calc 3, right, from space, the standard basis vectors. And their multiplication you could also think of as being some kind of weird, almost like a cross product type thing. And so this is how you defined the quaternions. So similar to how a quaternion is really could be thought of as some ordered quadruple of real numbers, A, B, C, D, that where these IJs and Ks have weird multiplication rules. You can define the Octonians. Okay, so these are the Octonians that are defined similarly, except instead of having 4 of these, you would have 8 of them. So the Octonians would be defined in a weirder way. I will mention them again later. I'm not going to write it out now. So the Octonians are similar to the Quaternions. Similarly, you have instead of having A, B, C, D, you would have A, B, C, D, E, F, G, H. Written like this, but instead of just having 1 I, J, and K, you would have 8 of those things with weird multiplication properties. What is the purpose of the Octonians? The Octonians are, they give me a number system, okay, that is what's called a division ring, but I'm not going to get into that. So the Octonians define a number system just like the Quaternions, except the Octonians are non-commutative. So multiplying 2 elements in the Octonians together, that multiplication is non-commutative and non-associative. Non-commutative and non-associative. So this is something that, if you haven't seen this before, this is almost certainly the first example of some kind of number system that is non-associative, right? Because even like matrix multiplication, right, is certainly associative. Most multiplications, most products of any kind you've ever seen are associative, at least. So in this case, the Octonians define a system that is non-commutative and non-associative. Okay, but it is alternative. What does alternative mean? Well, I'm kind of running out of room here, so let me write on the next page. So the Octonians are a number system. Like I said, I'm not going to go over the definition of them right now. You can, if you can't wait until we talk about them later, you can Google what these things look like. There's last I looked, there's a pretty big article on them on Wikipedia. So the Octonians, they're non-commutative, non-associative, but they are alternative. But they are alternative. What does that mean? So alternativity is the following property. It means A inverse times AB, associated in this way, is B, which is also BA times A inverse. This is the Alternativity Law. Think about this for a second. To think about why this is weaker than associativity. Okay, so commutativity is AB is equal to BA. So that's not the case for every A and B in the Octonians. Associativity means that A times BC is equal to AB, or sorry, A times BC, yeah, is equal to AB times C. That's not true for every A, B, and C in the Octonians. But for every A and B in the Octonians, I have an inverse like this, an A inverse, and doing this multiplication this way, so A inverse times AB is B, and that's also BA times A inverse. This is known as alternativity. Okay. Well, I can construct OP1, just like I constructed RP1, and even though I didn't mention it, I could construct HP1, that is, the Quaternion projective line. Okay, but I can also construct OP2. Okay. And when I construct OP2, this is the Octonian projective plane. Okay. So when I construct OP2, this is the Octonian projective plane. And what does this thing satisfy? So going with this same analogy that we've been talking about this whole time, since the Octonians are non-commutative and non-associative, the Octonian projective plane, assuming that I construct it in the exact same way, what kind of plane is that going to be? Well, since the Octonians are non-commutative, I'm not going to have a commutative property, so then there's no Pappus theorem. Since it's non-associative, I'm not going to have a Desargues theorem. So it's non-Pappian, non-Desarguian, that's an easier way to say it. So this is a non-Desarguian plane. So no Pappus, no Desargues. I can write that up here. I can say, so no Pappus. That's what non-commutativity means. And no Desargues. That's what non-associativity means. So this is a non-Desarguian plane. Okay, but it is alternative. When I say it is alternative, what do I mean? I mean that the multiplication that I define on OP2 in the same way that I defined multiplication in our projective plane is alternative. It's not associative, it's not commutative, but it's alternative. Okay, it is alternative. Well, if Pappus is associated with the commutativity law, and Desargues' theorem is associated with associativity, what is the alternativity law associated with? It's associated with little Desargues, i.e., OP2 satisfies little Desargues. So it is an example of a projective plane that is non-Desarguian. So it doesn't satisfy the Desargues theorem, doesn't satisfy the Pappus theorem, but it does satisfy little Desargues, and that gives you alternativity. Okay, so the multiplication is alternative. Okay. Now, just to quickly remind you, for all of those other constructions, right, we could start with RP2, we could construct RP3 and RP in any projective spaces we wanted to. We could do the same thing with the complex numbers. We could have CP2 all the way to CPN. We could even do it with the Quaternions. Even though the Quaternions aren't a field, we could construct HP2, which was non-Pappian plane. And we could construct the Quaternion projective space, HPN. That was perfectly fine. Let's try to do the same thing for OP2. Well, it turns out that OP3 does not exist. In fact, none of the higher Octonian projective spaces exist. So this does not exist for n bigger than or equal to 3. So in fact, other than OP1 and OP2, you can't get any other Octonian projective spaces. Why? This is an extremely subtle and very strange and interesting fact. So here's the reason why. Okay, there is a fact. The Desargues theorem is true in any projective space so I'm going to call our projective space say Pn. Okay, so maybe it's RPn, maybe it's CPn, maybe it's HPn, maybe it's an n-dimensional space of, or projective space of some other construction, but it is an n-dimensional projective space defined in that same generalized way that we did to define RPn and CPn. The Desargues theorem is true in any projective space Pn with n greater than or equal to 3. And so, anytime you're dealing with a projective space, the Desargues theorem is true unless n is equal to 2, i.e. for projective planes. So projective planes are the only examples of projective spaces where the Desargues theorem can be false. So that's another way of saying this. So i.e. projective planes are the only projective spaces where Desargues can fail. Well, you might look at this and say, how can that be, right? How can this be the case? Let's see what the spatial Desargues configuration would look like. So we are going to, this picture I'm going to show you is going to assume that the two triangles involved are in different planes. If they are not in different planes, it's a little bit trickier, but all you have to do in that case, if they're not in different planes, is basically you have to say something about one of the planes can be thought of as a shadow, or sorry, one of the triangles in the plane in question can be thought of as a shadow of another triangle in space, and then you're actually in the previous case. Okay, and so the main case here to take note of is the following. It's this one. So I have two triangles in space. And these two triangles are configured in this way, so they're not. These two triangles are not in the same plane. Okay, so I have two shaded triangles. What do I do? These lines here, these projection lines, are me drawing lines through the corresponding vertices of these triangles. Okay, and so now I'm drawing lines. I'm extending the lines of these triangles, the sides of these triangles I'm extending. So here I have this corresponding side for this triangle, the bottom triangle. I extend both of those sides and they meet on some line L. If I extend two other corresponding sides, they meet on the same line L. And then if I do the same for the third pair of sides, they meet on the same line L. Okay. And so this is the spatial Desargues configuration. Right? So it is saying the same thing, that if you have two triangles and they're in perspective in this way in space, then they are in perspective in another way, which is if I draw the extension of their corresponding sides, those all meet on some line. Okay, those all meet on the same line. It turns out that I don't need anything for this to be true. All I need are the projective space axioms. Okay, so if I have those projective geometry axioms for space, for dimensions 3 or higher, I get this. And it would be harder to visualize this for higher dimensions, for 4, 5, and 6 dimensional projective space, but it actually works in the same kind of way. Okay. And so Desargues' theorem is always true for projective spaces of dimension 3 or higher. So why does that prevent us from having an OP3 here? Well, suppose OP3 existed. Then Desargues would be satisfied. So Desargues would be true in OP3. Right? By that fact that we just said. But then the multiplication we construct would be associative. And if we've constructed multiplication on OP3, using our straight edge in this way, we can do these constructions. You might balk at this for a second because this is a construction in three-dimensional space, but we could actually carry over these constructions very similar way. So we construct a multiplication that would be associative. Why is that a problem? But O is not associative, right? The underlying space is not associative. So this is impossible. Thus, OP3 can exist. Okay. Okay. So this was a slight detour here at the end to take care of some very niche things, but it's nice to see these things because this is this is something that is an obscure enough fact that this is, if you don't see it now, then you're probably never going to see it. So now you have seen it. Okay. So that's that. These are some very interesting things that crop up with these with the particulars of these constructions. So now I want to move on to the last pillar of geometry we're going to talk about. Right, our textbook is called The Four Pillars of Geometry, and we've just finished the third pillar. So this was compass and straight edge constructions, right? The Euclidean geometry stuff. That was chapters 1 and 2. Chapters 3 and 4 were vector geometry, or linear algebra. That's the second. That was the second pillar, right? Vectors and coordinates brought in from the outside. And the third pillar was projective geometry. So we started out, right, by considering projective geometry in the way that it was developed by artists, and then brought into straight edge constructions, which led us to our construction of a generic projective plane, and eventually RP2 and RP1, right? And then from there we actually constructed coordinates using projective geometry. So rather than bringing them from outside in, right, bringing numbers from outside in like we did in chapters 3 and 4, we actually developed all this from within projective geometry. And that's what we just did. And so now the fourth pillar. What is this? This is Klein's Erlangen program. So it's named Klein's Erlangen program because he was at Erlangen University. I can't remember the full name of it when he did this. So this is from 1862 or 1872, sorry. That's when Klein did this. So this is Felix Klein. Klein's Erlangen program, that is the noticing that transformation groups were kind of the key thing being studied in geometry. This seems like a completely backwards way of thinking about geometry, but it actually yields kind of the most clarity of any approach of studying geometry. And the most important thing about it is that it allows you to study multiple kinds of geometries all at once. So before I get too much into that, I will say, so first of all, what are our examples that we think about? So let's think about some examples from our past here, right? So we've seen Euclidean geometry that arose out of, so we saw Euclidean geometry arising out of compass and straight edge constructions. We saw vector geometry, okay, that we developed next. Of course, we use the vector geometry to eventually prove some Euclidean geometry stuff, and projective geometry. Okay. Now, without really saying that these are different geometries, the main things we can notice is that for, say, projective geometry, right, what were the important things? So what were the important components? So important objects in projective geometry. Well, the important objects were straightness, right? Which you could also say is collinearity. Okay, maybe that only has one L. That doesn't look right. Okay, so straightness or collinearity are the important concepts, I should say, maybe rather than objects. But this is really the main important thing about projective geometry. Of course, we also saw that we were able to figure out some other objects that were important because they preserved these things. Okay. Now, we had other quantities coming out of projective geometry, namely the cross ratio, right, on RP1. So cross ratio was another important thing in projective geometry. Okay, and it turned out, of course, that if we looked at the transformations of projective geometry, what were these transformations? These were projective transformations, right? Embodied by the linear fractional transformations, right, or combinations of them. So projective transformations were our transformations for projective geometry. What did these things do, right? These preserved straightness or collinearity, right? And they also preserved the cross ratio. Okay. So then what is the Klein way of looking at geometry? The Klein way of looking at geometry is that we have transformations. We're calling them projective transformations. Okay, whatever. The point is we start with the transformation. So start here. Okay, so start here. Okay, so we start with our transformations. This is similar to what we did when we were doing RP1, right? When I was defining RP1, I actually defined the fractional linear transformations before I gave a definition of RP1 because they were included in the definition. So I needed to know what they were, first of all. And so we start with the transformations, call them projective transformations. These transformations fix or preserve straightness and cross ratio. They leave these invariant. This is another way of saying it. So projective transformations leave straightness and the cross ratio invariant. Or unchanged. That's what we mean when we say invariant. They leave these things invariant, unchanged. They preserve straightness and cross ratio. Another way of saying this is that straightness and cross ratio are invariant under projective transformations. That's another way of saying this. Okay. All right. So we started with transformations. We asked ourselves what quantities, what concepts, what notions are left unchanged or are invariant with respect to these transformations we started with. In this particular case, the notions of straightness and cross ratio are preserved. Really, of course, as we'll see, what's being preserved here is it's the concept of straightness, collinearity. Of course, the cross ratio helps measure that, but these are things that are preserved by these projective transformations. And then what do we do with that once we've figured out what things are invariant? This is where we move backwards. We say what is important are these concepts. What do I mean? I mean that the important concepts in the geometry in question are those that are left invariant by these transformations that I've picked. Okay, so in the normal way of thinking about geometry, I start with the geometry I want to study. I define what objects I care about, and then I say, okay, what transformations leave those invariant, right? This is what I did in Euclidean geometry, right? But the Klein way of doing this is I start with the transformations, I see what they leave invariant, and then I say those things that are left invariant, they are important in this geometry for these transformations because they are left invariant by the transformations. They're not important on their own. They are important because they're left invariant by these transformations that I've picked. Okay. And so the notion of straightness, collinearity, and the cross ratio are only important because those are the things that are left invariant by projective transformations. That's the Klein approach. So let's see how this works. So this was for projective geometry. Okay, and I'd already mentioned this before when we did it. Let's see how this works for Euclidean geometry. So here's another example, Euclidean geometry. So let's try to do this same approach, except now I'm actually going to write it in the correct order that if I'm doing Klein's stuff. So let's start out with the transformations. So what are my transformations? So my transformations are, and let's do Euclidean geometry of the plane. So let's do Euclidean geometry in R2. So we'll do Euclidean geometry of the plane. What are my transformations? Isometries of the plane. So isometries of the plane, which we are going to denote as isom of R2. All right, so this is the Euclidean isometry group of the plane. I'll define that word group here in a second. Okay, so isometries of R2. All right, so those are my transformations. Now, what do these preserve? Okay, what do these preserve? Well, let's think about it for a second. One, by definition, they preserve length. Right? The reason I say by definition is because literally that is how the isometries of R2 are defined. The isometries of R2 are specifically the transformations of R2, the maps from R2 to R2 that fix the length, that preserve the length. So by definition, they preserve length. Okay, and thus, I'm coming over here and saying, what are my important objects now? So, right, we're going in the correct order. So important objects or quantities or notions, concepts in Euclidean geometry. So what are these important things in Euclidean geometry? Well, length is one of them because it's preserved by isometries. Okay. Now, that is how isometries are defined, but it turns out that even being defined as just something that fixes length, this is not the only thing that is fixed by isometries of the plane. All right, what do isometries of the plane also fix? Angle. Right? If I have an angle given to me, right, in the plane, or in any Euclidean space, but we'll say the plane right now, so here's my angle. Well, I can rotate that angle, can translate that angle, I can reflect that angle. I can do combinations of those, glide reflections, whatever I want to do here. and that angle is unchanged, right? At no point do I squish these together or pull them further apart, right? Using isometries or combinations of isometries, I have that angle fixed. So even though isometries were not defined, angles are not mentioned anywhere in the definition of isometry, but it fixes this. So angle is an important concept in Euclidean geometry because it's fixed by these isometries. What else is fixed? Straightness, right? Just like for projective geometry. The notion of straightness, what do I mean by that? I mean, if I have a line and I apply an isometry to it, well, I still get a line, right? So lines map to lines, right? And so straightness of lines, that's something that's important in Euclidean geometry for the same reason. Okay, what else? Well, what about circles being circular, right? Meaning if I have a circle, so if I drew a circle here and then I applied Euclidean isometry to this sheet that it's on, would it still remain a circle? Yes, right? So circularity, we'll call it circularity. That is circles mapping to circles, right? That's something else that we get. And so this basically tidies up everything we have. Straightness in circles says something about having lengthened, that is a straight edge and a compass. Same thing with length and angle, right? That's really saying you have the notion of compass and straight edge that's hidden in there somewhere, right? Notice that if we go back to projective geometry, we don't find as important objects, all we have are straightness and collinearity, and the cross ratio is a thing that are important. But if we look here, length, angle, circularity of circles, none of that's mentioned here, right? Because in projective geometry, the projective transformations do not fix length, angles, or circularity of circles, right? So if you take a projective transformation and you apply it to a circle, do you get a circle out of it? No. You don't. Not necessarily. If you take a projective transformation and apply it to some length, does it distort the length? Definitely, right? Yes, it can certainly do that, okay? It is not guaranteed to fix the length at all. Does it preserve angles? No. Right? Projective transformations do not preserve angles. Okay? So projective transformations don't preserve any of those things. The only thing they preserve is straightness. And so for projective geometry, the only corresponding notion that is important is straightness. The only thing kind of like length that gets preserved is the cross ratio, right, as we saw before. So that's the thing to note. Now, Klein's big realization was that different types of groups were associated with different types of geometries. Now I'm saying geometry is plural, so I'm going to put scare quotes around it because the question is like, what is that? And what do we mean when we say geometry is plural? So before I talk about that, I'm going to define groups, okay? Because what it turns out is that our definition here, or our concern with transformations, leads us to consider sets of transformations, but not just as sets containing those transformations, But sets containing those transformations that naturally have a binary operation on them that satisfies a lot of nice things. Okay, these transformations, they arise as sets of functions, and kind of the most natural sort of operation you can consider for functions like this is composition of functions. So I'm going to do something. This is actually done at the end of chapter 7 in the textbook. I'm going to do it now. And I'm going to give a quick definition of an abstract group. Okay. So definition of a group. This is a mathematical group. Okay. So if you've had a course, a first course in algebra at the undergrad level, then you will have seen groups defined in this way. This will actually be more or less the first thing you do in algebra. So what is a group? A group G is a set. Okay. And we'll say that it's non-empty. I'm not going to even write that, but we'll say that it's non-empty. So it's a non-empty set G equipped with a binary operation. What is a binary operation? So that I don't spiral into giving you a million definitions. Binary operation is just an operation defined on a set G, in this case, cross itself. If it's closed, then that maps to G. So a binary operation is defined on G cross G to G. And a lot of times this will be called star for a group. And so if I have something in G called little g, and I star that with H, or maybe I should, here, let me write that. Let me write this differently. This is confusing. So if I have an ordered pair GH, right? If I have a pair GH, both of these are in G. This gets mapped to some element in G that is called G star H. Okay. All right. And the fact that this always goes to G, so I don't take two elements of G, star them, and get something somewhere else, that's called a closed binary operation. In this class, any binary operation I'm going to consider is going to be closed, so I'm not going to make a distinction. So a group G is a set equipped with a binary operation like this called star. So we'll call it star. That satisfies the following properties. Okay, so it's a list of three things. So 1, star is associative. Okay, what does that mean? Well, it means that G star H star I is equal to G star H star I associated in that way. And this is true for all G, H, and I in G. Right? So for all G, H, and I in G. Okay, so our star operation is associative. Okay, second, star has an identity element. That we'll call E. And this E has to be in G. It can't have an identity element, but the identity element doesn't belong to G. That's no good. So it has to have an identity element. This identity element belongs to G. What does it mean for star to have an identity element in G? It means that G star E is equal to G, which is equal to E star G, and that has to be true for all G in G. Okay, so there's an identity element called E. When I star any element of G with E, I just get the same element that I started with. So this is my object that behaves like 1. Okay, of course, you've already seen the concept of an identity element before. This was with the field axioms. And then lastly, the last thing that's required, each element in G has an inverse relative to star. What this means is that for all G in G, there exists something called G inverse in G, such that G star G inverse is equal to that identity element E, and actually it works in either order. Okay, so there's my 3 things. Now, you're naturally going to have some questions here. So, 1, you're going to note, wait, isn't a group basically just like it's just like a field, except it doesn't satisfy nearly the same number of axioms? That's true. So 1, note that a field requires 2 binary operations. It requires a plus and a star, right? It requires a plus and a multiplication. Of course, we've used star here. The reason we've done that is because the examples of groups that we're going to think about, oftentimes what we talk about when we talk about the group, it's going to be a multiplication is going to be our star, and sometimes an addition is going to be our star. So just because this is a star doesn't mean it's always a multiplication. It is just a binary operation. So for instance, one of your easiest examples of a group, take the integers with plus, right? Take the integers, take the operation of plus, that's a group, okay? Adding integers is associative. And integers have an identity element with respect to plus, that's just 0. And each element in Z has an inverse. So, everything has something you can add to it to make it 0. So for integers, that's just minus the integer. So 5's inverse is minus 5. 0 is its own inverse because 0 plus 0 is equal to 0. Okay, so the integers with addition are kind of the simplest example of a group. Okay, and there we used plus for our binary operation. Okay, and so this concept of group, you'll hear this over and over again. Kind of the popular, like the pop math description is that groups encode symmetry in some way, and that's certainly true. And that's ultimately what we do with them here. Is that as it turns out, these transformations that we talked about, if I consider them as a set, and the star operation I take, I consider that to be function composition of functions, then those sets of transformations for Euclidean geometry and for projective geometry, they are groups. Okay, they are groups. And so they are transformation groups. And so what Felix Klein noticed was that associated to different types of geometries are different types of transformation groups. Okay, so we'll talk about that next time, and I'll give some examples about how you can change the group a little bit to change the geometric considerations of what's going on. Okay, so anyway, we'll talk about that next time. So remember, today I have office hours. I will send a link. I will put a link in the announcements later today. So that's from 3 to roughly 4. I'll leave a little bit early, so it's more like from 3 to like 3:55. So anyway, I will see you then.